Good morning, rockhounds and rockheads. Laura from Rock Your World coming right at you with Feldspars finally. I know, right? It's taken me so long. What's true is that feldspars are actually really complicated. A lot of people don't really understand them. It takes some chemistry knowledge, which, yeah, I did so great in that in high school. But as a practicing economic geologist, I've gotten much better. So we are going to get into feldspars and why they are so prevalent on the crust of the earth. Why almost 50%, if not more, of minerals we find are of the feldspar group. They're more prevalent than any other mineral on the crust of the earth that we can find, and even in the ocean crust, it's really all over the place is all I can say. So I've already bored you. So we're gonna do a test, and I'm gonna see if this works. You see my little diagram there? I'm gonna test this out. All right, this is how it started. I got me some Sunstone, moonstone, and I was like, well, WTF? I guess we really need to get into feldspars, because if I don't understand them, there's a large likelihood most people don't understand them, except for people who have taken mineralogy. And then, yeah, I've had some conversations with people who don't understand them too. So I'm going to try to break feldspars down for you so that you can speak from a place of knowledge. First off, this is a trade mineral or trade name for feldspar. For one of the types of feldspar, there's multiple types of feldspar. We call this sunstone moonstone. Isn't that confusing? It's super confusing, so that's why we started this journey. So in continuation of feldspar education, first we're going to go over what a couple of these things are in case you're not familiar with the terminology. So there is a stone. It is called amazonite. It's blue. It is a form of microcline. Pardon me, microcline is an alkali feldspar, and it will be at the top of our pyramid. It occurs usually in granite and other intrusive or volcanics that harden underground, and it is blue, at least amazonite is, because lead has replaced some of the ions in it. Yeah. So this is a piece of moonstone. Let's see if we can get it to flash. It's been carved, it's white, and most likely this piece of moonstone is going to be closer to labradorite in its chemistry, but not all moonstone is just white labradorite. In fact, moonstone is a trade name. There's silky moonstone, there's rainbow moonstone. It can actually occur as, essentially the definition is a white to tan base, okay? It's got a flash or an aldorescence to it. It displays kind of a schiller. It can be a silky schiller. It can be a colorful schiller. Moonstone is a very loose definition. In fact, it's one of our loosest definitions we have for any stone of the feldspar family that we use for jewelry. So, because it's a trade name, it's not the stone's name. It doesn't talk about the chemical composition. It doesn't even talk about where it came from. It is a white to tan stone with a schiller or aldorescence, meaning that flashy flash. And we'll get into what causes the flashy flash, I assure you. Stay tuned. So it cools slowly. That's one thing that moonstone needs to do in order to what's called exfoliate, or create layers of different kinds of feldspar, one layer after another after another. And they can be different kinds of feldspar. When different atoms can hang out in the same crystal, it's called a solid solution. I thought solutions were only wet. No. When two atoms of two different materials can hang out together in a solid, it's called a solid solution. So this is a solution of multiple types of feldspar. And we know that, if I can get it to flash here, you can kind of see that little blue. This is actually a better moonstone than it's showing up has. So you have this exfoliation, meaning a layer one kind of feldspar, layer another kind of feldspar. And they can be dramatically different on this pyramid scale I'm going to show you. So first feldspar, moonstone. The other thing about moonstone is that a lot of it is mentioned in like 100-year-old mineralogical surveys. What they were experiencing, there's no pictures. So the name moonstone has grown as crystal trade and jewelry trade has grown. And so what someone may have called moonstone 100 years ago might be something different now, or we've lumped a bunch of different moonstones into that category. So that's something that you need to understand, is that a lot of this information is old. The other thing is that Wikipedia is not a good source of information. In fact, I even found some misinformation on Mindat, which that's usually the go-to. But what's true is a lot of people don't understand feldspars. So what is a feldspar? It contains aluminum, silica, oxygen, and different proportions of other minerals, primarily potassium in our alkali feldspar family, sodium, and calcium. Those potassium, sodium, and calcium can be replaced with other more rare minerals. However, I guess elements, those are very rare. I do have some rare feldspars that I am going to do videos on, like rainbow lattice, sunstone, and things of that nature, but they're going to come a little later because feldspars are super complicated and I want you to understand them before we move on to the next. So feldspar being like over 50% of the minerals being found on Earth, 50 to 60%, about 12% are alkali feldspars, 39% are in the plagioclase family. Now don't worry, I have a diagram. It is coming. They are a tectosilicate, meaning that they are SiO4. They form in a tetrahedron, and some of it is replaced by aluminum. And so that's what we call distribution in feldspars. And it's divided into high or disordered feldspars and low or ordered feldspars. The order is related, as I said, to the randomness of the aluminum ions, and the order improves with decreased temperature. So what that means is as the aluminum settles down faster or slower, it can allow for other minerals to be added, or elements to be added to this chemical composition of the feldspar and change the dynamics of it, or make different layers of it, as we talked about, a solid solution. You can have one kind of feldspar, then another kind of feldspar, then another kind of feldspar, then another kind of feldspar. And that's what gives us the flashy woo-woos, is that exfoliation. So if you want to understand why you have that flash, it's because feldspar can make a solid solution, meaning two different minerals in one crystal. It's crazy. So with that, it's a bit complicated, as I said, and there are generally three groups of feldspars. There is the plagioclase, which primarily has sodium to calcium levels in addition to their aluminum, silica, and oxygen. And then there's also our alkaline feldspars, which go up in potassium content. When you move away from a lot of sodium and you move into potassium, there's a range where it only forms at really high temperatures. That's called sanidine. And a lot of alkali feldspars are used in ceramic production. Also plagioclase feldspars. Feldspar, they use it in the glaze, they use it to stabilize the ceramics itself. That's the primary industrial use of feldspar. We use it as jewelry. So the three types of feldspar are plagioclase, as I said, and which is albite to anorthite, so sodium to calcium. There is alkalkic, meaning that it has a potassium or sodium content, and that's albite to alkaline or potassium feldspars. And then there's a barium and other rare element type feldspars. Those are very rare. We're not really going to talk about them. We don't really use them in jewelry, but they do occur. Now, amazonite is a microcline. Now, here's a nice big solid chunk. And amazonite is often mottled or striped, meaning it's splotchy or striped. I have another piece right here. And this is a potassium-rich microcline with stripes. The white stripes are albite, or the sodium-rich feldspar. We get a schiller in this stone. If I can get it to schiller on us, it will flashy flash a little bit. I know I have other pieces that do. But amazonite can have a schiller to it. It's a combination of microcline and albite. That's what those stripes are. And the blue in amazonite is actually from a lead replacement in the chemical composition of it. It will replace some of the potassium with lead, and that way, that's how it turns blue. So essentially, colors are produced when exposure to geophysical radiation deforms the lattice and creates voids, which are called color centers. These color centers trap lead ions, altering the light absorption characteristics of the amazonite, creating this blue-green effect. Albite, once again, sodium-rich feldspar, creates the white stripes, and the rest is microcline or potassium-rich feldspar. Trippy, huh? So this is one of my best examples of albite. This is Sunstone, Moonstone as the trade name is called, but it's pististorite is the name of this stone. It also, there's other trade names, some Russian trade names, but we're just going to call it Sunstone, Moonstone. But pististorite is almost solid albite. It is in the albite family. It only has some laminations of a little bit of some kind of other feldspar, which nobody knows. Nobody's been able to tell me what's the lamination, what's the exfoliation. However, this is going to be a sodium-rich feldspar. Sunstone, Moonstone usually has a white to tan base with a blue flash. A lot of it comes from Russia, but there are other places it comes from. And in Russia, it's called belomorite because it's from the Belomor mine. However, pististorite or Sunstone, Moonstone is what they're calling it on the market, and it's a tan base with a blue flash. This is an albite family feldspar. So, we're going to get into sunstones. First, we're not going to talk about Oregon sunstones. We're going to talk about what we call Indian or adventurine feldspar. It's got these glittery guys in it. It's usually a red, orange color, and the glittery guys are from goethite or little iron inclusions. Now, these are often an ogleclase feldspar, with tiny muscovite or hematite inclusions, making a green and orange glitter. So this is not related to Oregon Sunstone. I mean, like, yeah, they're both feldspars, but these adventurine feldspars, or what we call Indian sunstone, they can occur all over the world. They don't just occur in India. They occur up in, like, Norway, things like that. Pretty much all over the United States, there's a lot of places where this sunstone has shown up, and most of it is a microcline. It can be either ogleclase or microcline, but that's what I'm finding out, is a lot of this sunstone is microcline, which is crazy, but true. So, stick with me. We're going to find some more. All right, now we're going to get a little bit crazy. We're going to talk about labradorite. And the first type we're going to talk about is the Oregon Sunstone. Oregon Sunstone, here's an example of it. It's going to be a tricksy one. There's that guy. Let's see if we can get it to focus. Focus, there we go. Now, these both might be called sunstones, but they're formed in completely different ways. This sunstone is an ogleclase, or it can be a microcline, but it is not. It is not the same chemical composition as an Oregon Sunstone. It is farther away, it is more alkaline, it has more sodium, and potentially more potassium, and formed in completely different ways. This comes out of lava, this comes out of the ground, hardened as a crystal already. This does not come out extruded in magma, but this Oregon Sunstone does. Now, I've done enough research into this to tell you that yes, Oregon Sunstone is a labradorite. But as we were talking about high feldspars and low feldspars, disorganized versus organized, sunstones are less organized than labradorite that we have come to know. It's one of the reasons why they will have a limited schiller, and the schiller often comes from a metallic inclusion like copper, sometimes aluminum, and it can also just have that schiller effect if it gets what's called that exlamination. But because these form in magma and they form at high temperatures, they are more disorganized, so they don't make that this, then that, then this, and that, then this, and that. How do we know for sure Oregon Sunstone is a labradorite? Well, a scientist did a sciencey thing about it. There's a paper, and on the albite to anorthite scale, which we'll get into, it's a hard 67. That puts it right in labradorite land, 60 to 70% anorthite. The interesting thing about sunstones is in the matrix, in the rock it occurs in, the basalt. The other little plagioclase crystals can be anywhere on the plagioclase spectrum, but it's only these bigger crystals that contain the color, or just even the bigger crystals, that come in as a labradorite. The others can be anywhere in the plagioclase family. Bitonite, andesine, anorthite. It can be a lot of different types of feldspar surrounding these chunks of labradorite. That is how sensitive feldspars are to how they form and what they're going to be. So what is an Oregon Sunstone? It's a 6.5 on the Mohs scale of hardness. It has copper in it, but it also has other minerals, which we're going to get into. I'm in contact with a doctor who has studied these, and I'm getting into the blues, purples, greens, pinks, reds, oranges, what causes all those colors. We know copper, but we also know that there are some other minerals that are causing those colors. So to answer your question, yes, Oregon Sunstone is a labradorite, and places like Mindat and Wikipedia will mislead you. There's a lot of misinformation about sunstones. The information I'm giving you today is from scientific white papers by scientists who have chemically tested this stuff. So yes, Oregon Sunstone is a labradorite. It's good for jewelry. It does have it's called a distinct crystal cleavage, like all feldspars, so meaning that on those layers it will break. That is the most likely way it will break, is upon the crystal layer, and not chip like glass or something of that nature. It will break along the crystal lines. So there's information on Oregon Sunstones, and we'll get into more, I promise. I'm going to go back to this piece of moonstone just as an example of something called Agilia. Now, I have Agilia at my mine. Agilia can occur in two places, probably more, but two really distinct places. The first place is in quartz Agilia deposits in a low sulfide epithermal deposit. What the hell did you just say, Laura? So low sulfide means there's not a lot of sulfide minerals. Epithermal means hot water or groundwater, warm groundwater. So it can deposit from dissolved minerals that's circulating around, and it comes out of solution into a solid solution, and you get Agilia. The other way you get Agilia is from, essentially they find it in like granite and really high peaks. And that type of Agilia, some is orthoclase, but some has become microcline. That just means that it's shifted its crystalline structure, and it can occur in alpine areas. So essentially what happens is the body of magma hardens away underground, and then over millions of years of uplift and erosion, it has made it to the top of the mountain. And now we're finding it because it's exposed. And we'll find a big piece and we'll be like, ooh, shiny. And it's the type of feldspar that occurs in a lot of granites and granodorites, which is a microcline mix. So that gives you some information on what Agilia is. It's the base word for alderescence. and it's a type of moonstone. I have Agilia on my mines, and I will be producing more. I'm actually headed out there soon to go get some, and it has like an orange, yellow, pink flashback to it. It's really cool stuff. So I'm just using this moonstone as an example, a hold-in piece for Agilia. So I just used a term for the flash called aldorescence. So the blue flash is what we call aldorescence. It's in moonstone, it's in sunstone, moonstone. It can be in labradorite, it can be in any feldspar. And most of the time it's in the orthoclase to albite, so potassium to sodium feldspars. It can occur on occasion in plagioclase. However, when we call it aldorescence, it's usually in the sodium to alkali feldspars. That's where the sunstone, moonstone, which is a primarily sodium or albite feldspar, comes in. And what it is it's the slow cooling of feldspar minerals that allows the exsolution laminae, is what it's called, that makes these layers or intergrowth of different types of feldspar to form. So it's commonly like albite mixed with a little bit of plagioclase or a little bit of microcline or orthoclase. It's one then the other, then one then the other, then one then the other, just like this aventurine. Or not, this isn't aventurine, amazonite. Sorry about that. See the stripes? That's that exfoliation. Cooled very slow and allowed it to separate, but make one crystal. One crystal of multiple minerals. So what's with this like ion switching out thing? What's with this calcium, potassium, sodium thing? So the IMA has classified feldspars into only 3 names, but there's a lot more names for that, depending on how much calcium, sodium, or potassium is in them. So the 3 main types, according to the IMA, are a K feldspar or potassium feldspar. There is albite, which is a sodium feldspar, and anorthite, which is calcium feldspar. And different proportions of these throughout the crystal, because feldspars can make a solid solution, are what makes the different type of feldspars. So when we get into it, why does that happen? Why is only 12% potassium alkali feldspars, where 39% of the 50% to 60% of minerals that are feldspars? Why is it so easy to form plagioclase or switch out the plagioclase as opposed to the potassium? Okay, gonna get a little nerdy on you. What's true is that a sodium ion and a calcium ion are about the same size. It's really easy for them to switch places. It's very easy. They're very similar. Potassium, however, is very big. Sodium is a little small. It is small like the calcium is. So for the potassium to wedge itself in there has to be something like heat, pressure, time, and different chemical settings in order to wedge that potassium ion into that chemical structure. And it's why the potassium or alkali feldspars are less common. Labradorite. See the stripes? So this is from exfoliation. Labradorite is anywhere between 50% and 70% anorthite or 30 to 50% albite. It cools slowly underground, and so that's when we get these exfoliation laminae. So what you see here is a layer of one kind of feldspar and a layer of another kind of feldspar. Labradorite comes from all over the world, from Canada, Norway, Madagascar. A lot of older metamorphic rocks are what shoot up this type of labradorite. Now, these are both labradorites. The difference is disorganized, organized, disorganized, organized. Comes from liquid magma, comes from deep underground as a metamorphic stone. But this is 67% anorthite, and this is somewhere between 50 and 70% anorthite. They have the same chemical composition, they just formed in 2 totally separate ways. Alright, so here it is. Here is the diagram I drew. I drew it to look at this diagram. Alright, so here we go. Let's do it. So we have sodium down here on the bottom. We have potassium up here, K. Sodium, Na, and calcium, Ca. And there's some words that you might recognize here. So we have microcline up here. That's going to be our amazonite family, okay? Then we come down here, got our albite, anorthoclase, and anorthite. So these are albites that start to get into having some potassium in them and start to get into having some calcium in them. After that, we have andesite, labradorite, biotinite, and anorthite. Now, what's this big space here? This is a big space that feldspar just cannot form in. It has to have this balance in order to form. Most of the feldspars that we run into in jewelry are going to be in this category or way up here in microcline, like our amazonites and some of our agilarias. Agilia is usually this plus this. So that's the moonstone. But moonstone, once again, is any white feldspar that shows an aldorescence or a blue or colorful flash or even a silky flash. So we recognize some words here. Here's labradorite. It is right here in here, which is where also our sunstones land. Now, why is it that our sunstones don't flash like labradorite? It's because labradorite has had time to cool underground and exfoliate and have its different layers of sodium, calcium, sodium, calcium, sodium, calcium. Build that crystal. And that's where you get the vivid colors from. So I'm going to zoom in on this for you. I'm going to give you a moment with it. Feel free to pause. This is feldspar. There will be more feldspar gemstone videos, mostly because I need to find a couple of specimens, honestly. I was showing off my piece of rainbow lattice moonstone and kind of wandered away. But recap, okay. Moonstone. Any white feldspar showing aldorescence or schiller is what moonstone is the trade name for. What is it? It's a feldspar. Probably more likely in the plagioclase family and albite than anywhere else, but it can be in the microcline and orthoclase family. I wish I could get this to flash better, but it's just not behaving. So, moonstone, white feldspar. Don't know exactly what it is. Anyone who tells you exactly what it is better know where exactly it came from. Sunstone moonstone, mostly albite, mostly sodium moonstone with exfoliation layers of other feldspars. Most likely microcline, and that's where you get that schiller right there. And then you get that blue. And this is potesterite, albite, or sunstone moonstone. Labradorite. Organized, labradorite, disorganized. High temperature, lower temperature. Formed quickly, formed slowly. Both 50 to 30% sodium with 50 to 70% calcium. That's how these are both the same type of rock. Formed in magma, formed deep underground. Labradorite. Microcline. Many of our other sunstones are microcline. So is amazonite. It's had some lead replace some of the ions. These are both high potassium, usually form underground, and usually form in pegmatites and intrusive volcanics. And one of the things that all feldspars weather into is clay. So they are acid sensitive. They do have a distinct crystal cleavage. They do fracture on crystal layers is what that crystal cleavage means. And the 6.5 on the Mohs scale hardness means it's about as hard as steel. What these don't have, the more exfoliation you have and the more organized it is, you lower the tensile strength of the stone. So when I talk about tensile strength, it means the amount of strength it takes to push a stone like this or like that. So that's why when you have a quartz family mineral, often it breaks like a shell-like fracture, like when you break glass. However, when you break a feldspar, oftentimes it gives along one of those exfoliation laminates. So here's a piece of raw amazonite. See how it can be all chunky monkey? Co-occurs with quartz. Here's a piece of cut amazonite with those exfoliation layers. So there's a quick overview of feldspars, but I know there are more. What feldspars are you interested in?